Hello and welcome back. Let's discuss a bit how we can develop code. One option we've encountered so far already is using Jupyter notebooks, but we can also work with a local file structure and a project setup. So why would we do either of those? Jupyter notebooks are very versatile and convenient. They're very easy to use and they're great for exploring data, trying out some code ideas, plotting data and generally getting familiar with what we want to do. They're ideal to mix code and results and images and graphs, so they're really very useful for exploratory data analysis and they're also very convenient for teaching. This is why it's so often used. However, they also have severe disadvantages. In particular, they don't really have a defined state. The behavior of the notebook depends on the sequence of the cells we run in which order. So variables or functions may be overwritten depending on what we did earlier or we didn't do earlier. And if we sort of jump around the notebook, it's quite difficult to remember what we have already executed and what we still need to do. It's also very difficult to follow coding standards and best practices and to work collaboratively. We can't really add any proper documentation. Of course, we can mix text and code, but we can't write a proper documentation webpage, for example. It's also very difficult to do testing, and it's difficult to work in groups with multiple developers on the same code. There's also a lot of extra, well, it's not really bloat, but the notebooks persist a lot of information that is not really related to the code, and that is nice when we want to work interactively, but not so convenient if we want to work in a group or on a large project. So as a best practice, we can use notebooks for exploration and teaching, but we shouldn't really be using it for real, reproducible, stable code. So what should we be doing instead? Well, essentially we follow the same approach as we would do for other programming projects. We have a defined directory structure with source code, documentation, tests and so on. We have lots of files that we keep together and group them according how the code is related, and we use as small files and small units as possible. This makes it much easier to maintain and also refactor and optimize our code, but also to test and document our code using the right tools. This will then give us a stable and reproducible environment, and it also is much easier to track code developments in repositories. A sample directory structure is like this, so there is no really fixed mandatory structure or an enforced standard, but there are some recommended best practices. For example, our new project would be called My Project with capital letters, like my in capitals. And this is one of the conventions that we use, and the source code goes into a directory called My Project with all lowercase. Of course, you can also use src or source or something. So as I said, there is no fixed enforced standard, but most people tend to follow these. The tests for your code goes into directory tests, and then usually there's a file, a README file, either in Markdown or in other formats that contains information that is accessible to us humans. And there's typically a file called PyProject2ml that contains metadata about the project. Additionally, when we have auto-generated or manually generated documentation, that will go into doc, and a file called setup.py if we were to release our own software library, and a file called requirements text or equivalent for other packaging management systems will contain information on what we depend on. There are, of course, tools to help you with this. One of them is PyScaffold, another one is Cookie Cutter, and the package manager Poetry also does it as an example. So you have to get the tool that you find most convenient and that works best for you. Let's come to a point that is particularly painful for Python. It's not for nothing called versioning hell, because there are many Python packages available. This is a great advantage of Python because we can use so many different libraries for so many different applications. From databases to image handling to language processing to web development to machine learning to scientific computing, you name it. And there's a very large global community that develops in Python. However, of course, there is no central coordination agency that does this. And as a consequence, only specific versions or specific packages work together. And of course this differs from project to project. It's actually not just the Python problem, all other projects suffer from this as well. but because Python is so flexible, maybe we encounter this here first. So what can we do to remedy this? One of the options that we can use is using virtual environments. So we don't install all the libraries system-wide. Instead, we sort of create a protected environment, shall we say, where we install all the required packages and softwares into a local folder, and then only use this local installation, and we can use this for each project that we want to work on in parallel. So these don't mix and mingle, and we can well separate all the different packages and all the different versions. Again, choose the right tool. There are many of them available. The most important ones are virtualenv. This is like the standard Python approach to do it. It's almost always available, but it's not quite as powerful as others. Poetry is also a virtual environment manager, a packaging manager, dependency resolver, and as we just said earlier, it creates our scaffolding for a new project. It's quite powerful. And many people use Conda, which also handles many non-Python packages and dependencies. There's another one, Hatch, which admittedly I haven't used so far. So let's start with the standard way of doing things, the virtualenv. In the first step, we create a new virtual environment and we call it testenv and put it into some directory called virtualenvs in our local installation. And we do this by invoking the command virtualenv and give it the directory name where we want to have it. In our case, in virtualenv, in my home directory, virtualenvs, and underneath that we want to create the testenv. Now we have the minimal setup there, and to work in this new environment we need to activate it. So we call source, this is the command to actually then read the setup files for it and activate this. And then you see in the beginning of the command prompt bracket testenv bracket, that means that now we work within this environment and we are sort of isolated from other environments. Now we can install all the software that we require, for example NumPy, and we use pip for this here, and pip install NumPy, and then see is downloaded and installed into the local environment. This we do for all the packages that we require. We can also then export the list of all files and then put this all into a file called requirements.txt. And then once we have such a file, we can also just say pip install -r requirements.txt. And then this will go through and create all our environment packages locally. Then we can execute our programs on the command line as we would normally do.